Philip Roth and Fred Switzer III present Outliers and Influential Cases, Handling Those Discordant Contaminated Maverick Rogues. Outliers have confronted scientists in many fields for well over 200 years. They have earned titles such as discordant observations, rogue values, contaminants, and mavericks, and those are only the published or printed names. Like missing data, these data represent relatively common and persistent problems. However, unlike missing data, these data are likely to be more troublesome for two reasons. First, it is very easy to ignore outliers. Typically, researchers know when they have a problem when n drops from over 600 to near 200 as a result of missing data. However, outliers can markedly influence statistics with no easily observable signs. Second, there is very little empirically based guidance that helps researchers handle these values in applied psychology and related fields. The purpose of this chapter is to provide a conceptual overview of the field of outliers and influential cases that is accessible to a wide variety of readers. Outliers versus influential cases. The distinction between outliers and influential cases is an important conceptual issue, as it facilitates understanding the strengths and weaknesses of various outlier detection techniques. Definitional issues are somewhat problematic, as it is difficult to define exactly how far one or more data points are from other data in order to be an outlier, and how much influence on a given statistic one or more data points has to have to be an influential case. We define outliers and influential cases below and try to use these definitions throughout this paper. The term outlier or extreme observation is generally used to denote a case that is distinct from other observations. As such, there is generally no explicit requirement that such data points have a marked effect on a given statistic. All of the illustrative data points in figure 14.1 A to F may be thought to be outliers. Note that in all cases, the outliers have a substantial distance from the regression line that would have been computed based on the other data points. Before progressing further with our discussion, we note that there are two regression lines in each illustrative case in figure 14.1. A solid line is used to represent the regression line that would have been computed without the outlier. In contrast, a series of dashed lines is used to illustrate the regression line that is calculated with the outlier. The difference in the slope of the lines is important in delineating the concepts of outliers and influential cases. Returning to the outliers A and B in figure 14.1, statisticians label the difference between the outlying point and the rest of the distribution as distance. They note that distance is a necessary but not sufficient condition for a point to influence the statistic in question. Interestingly, cases A and B have high levels of distance, but are unlikely to influence correlations and regression weights. This lack of influence is a function of where these outliers are in the distribution. Their location near the middle of the independent variable distribution makes it impossible for them to increase or decrease the intercept slightly, but they are not likely to change the size of the regression weight. In essence, they can pull the entire regression line up or down slightly, but they don't change the slope appreciably in the illustrative cases, as can be seen by comparing the solid and dotted regression lines. In contrast, an influential case refers to an observation that by itself, or in conjunction with other observations, has a demonstrably larger impact on the value of a relevant statistic, that is, the correlation or regression weight, than other observations. An outlier or influential case can also be in a univariate, bivariate, or multivariate sense. That is, outliers or influential cases can have the above properties when analyzing frequency distributions, correlations, or in multivariate analyses such as multiple regression or MANOVA. We illustrate bivariate influential cases in figure 14.1c to F. One can see how an influential case, such as the one in case C, might markedly increase the regression weight, or correlation, to be more positive than the rest of the data would otherwise suggest. In essence, the influential case pulls the regression line up so that it has a steeper slope than it would have had if calculated on the rest of the data. The influential cases in D would likely minimize the negative slope. That is, it makes it more positive than it would have been if only the rest of the data were used to calculate the slope. Again, it is interesting to note that the location of these data points in the distribution of scores. Data points that are relatively far away from the mean score of the independent variable, as in C and D, have the opportunity to influence the calculation of a statistic and are said to have leverage. Influential cases thus require distance and leverage. Seems like it has to be far away from the mean value of x and the mean value of y. Influential cases thus require distance and leverage. It is important to delineate between the methods used to detect outliers and those used to detect influential cases. Statisticians in applied psychology generally worry more about influential cases than about outlier cases, as they focus much more often on interpreting regression weights or correlations rather than focusing on the intercept. The influential case in E has both distance from the regression line based on the other cases and high leverage. As such, it might markedly change the slope of the regression line and increase the correlation coefficient. Bobko shows that in a case similar to E, the majority of the data would result in an R of 0.14, but that inclusion of the outlying point would increase the correlation to 0.45 when there were 21 data points. This marked increase in the correlation is quite unsettling and illustrates the importance of considering influential cases. What is the typical approach to dealing with outliers? Given some familiarity with both the outlier/influential case literature and applied psychology, we suggest there are probably two typical cases for handling outliers. One case, which we believe to be common, is to ignore the issue. This may result from a lack of knowledge about the issue in many individuals otherwise well-trained in applied psychology. In the case of one author, the terms outlier and influential observation were not mentioned in his graduate education. Such a lack of familiarity may also be a function of the absence of rewards for finding and documenting the existence of outliers. This problem may exist for both academics in the review process and the practitioners when their work is evaluated by supervisors or clients. In both cases, the result is more skepticism of the results of one's research. A second typical case is to examine univariate frequency distributions for outlying values. Outlying values that fall outside the range of possible values are either deleted or checked for accuracy, and other values are typically accepted as likely to be correct given little further attention. Occasionally, a researcher might examine scatter plots of bivariate relationships to visually identify outlying values. This is an important practice, as observations can fail to be univariate outliers, but can be bivariate or multivariate outliers or influential cases. Thus, we recommend this practice to fellow researchers. While both of these approaches are quite helpful, there are a substantial number of techniques that allow more rigorous analysis of these potentially problematic data. Approaches to detecting outliers and influential cases. While the analysis of frequency distributions and scatter plots is a part of detecting outliers, there is more to the art of finding them. We explicitly note that this process is further along the continuum of art to science than many other statistical techniques, for example, interpreting in ANOVA, as there is much more judgment involved. There is also more of an interplay between graphical analysis and moderately complex statistical analysis than in other forms of analysis. In order to provide an overview of this area, we sample some of the more widely used techniques. We approach these techniques from a conceptual angle and refer the interested reader to an in-depth review in Boland and Jackman 1990, Chatterjee and Haiti 1986, McClellan 2000, and Netter, Wasserman, and Kuttner 1989. Univariate outliers. There are two families of approaches to finding univariate outliers or influential cases. The first approach is some form of graphical analysis. Individuals might look at univariate frequency distributions, box plots, stem and leaf plots, QQ plots. The common theme underlying all these graphical approaches is to visually locate an outlying value in a distribution or graph. For example, a researcher might be interested in using a cognitive ability test to predict job performance for a large accounting firm. Most of his or her data might fall in the range of 18 to 25. However, there might be one data point that has a score of 33. Stem and leaf plot would also immediately identify such an outlier. Individuals using graphical analyses have often used rules of thumb to identify outliers. For example, outliers are data points more than 3 standard deviations from the mean or more than 1 standard deviation from the next nearest data point. These rules of thumb have limitations. They don't take into account either the shape of the distribution or the role of change in producing extreme but valid cases. These rules can be arbitrary and may improperly exclude cases when used alone. Rather than encourage reliance on rules of thumb, we suggest that graphical analysis is a useful first step towards further investigation by more quantitative methods. The most common quantitative approach to detecting outliers is to examine the size of residuals. Again, we illustrate the logic of this approach within the framework of multiple regression, as there has been a great deal of work on outliers in this technique. Conceptually, the process of examining residuals is to compare the actual dependent variable y value for each observation to the predicted y value from the regression equation and divide the difference by an estimate of the standard error. For example, the researcher predicting job performance for accountants might increase the number of predictors of job performance to include tests of conscientiousness and biodata, as well as a test of cognitive ability. That researcher might have a sample of 300 individuals for which he or she has data for the 3 predictors and a measure of job performance. One approach to the analysis of the accountant data would be to conduct a multiple regression in which job performance is regressed on the 3 predictors: conscientiousness, biodata, and cognitive ability, as well as independent variables. The researcher could use virtually any statistical program, including Excel, to request analysis of residuals. In some form, the printout will display a t-value for each of the 300 individuals in a sample size, the t being the results of dividing observed y minus predicted y by a measure of standard error, as described by Chatterjee and Haiti, 1986. The attained t-value for each case may be compared to a t-value with n subtract k subtract 1 degrees of freedom, where n is the sample size and k is the number of independent variables, to determine which values are outliers. This approach is typically called studentized residuals, since the resulting values are distributed according to a student's t-distribution. There are several things to note about student-sized residuals to detect outliers. First and most importantly, this technique is designed to find any outlying observation regardless of influence on the statistic of interest. That is, this approach will detect outliers such as those in figure 14.1 that don't have a great impact on the statistic of interest, for example, cases A and B. This is because the technique focuses solely on distance, but does not conceptually incorporate leverage. Second, there is some debate over how to estimate the standard error. The most prevalent approach is to calculate the standard error without the case in question. For example, our researcher predicting accountant job performance might be looking at the residual for the job applicant, Madeline. Typically, Madeline's data would not be used when computing the standard error. This calculation of studentized residuals without the case in question is sometimes referred to as an analysis of studentized deleted residuals. Third, the focus of this approach is typically on the entire regression equation. If the researcher is interested in interpreting each regression coefficient in a multiple regression equation and is worried about undue influence on one or more of the partial measures of covariance, this technique may not be optimal. Finally, the use of a statistical test of significance using n subtract k subtract 1 degrees of freedom and some level of alpha will be highly likely to find some outliers just by chance. For example, we might set alpha at 0.05 and estimate 20 observations. We are likely to find at least one outlier just by chance. As a result, researchers may use a given alpha level as only a rule of thumb and start to examine the outlier with the largest t-value first. Or they might adjust alpha by apportioning it across the number of comparisons, as in the post hoc test of significance of ANOVA. Bivariate and multiple variable analyses. Univariate analyses of outliers and influential cases provide an interesting place to begin both discussion and analysis. However, most analyses in applied psychology involve at least 2 variables. Thus, we turn our attention to this area, but first we clarify the importance of outliers in independent versus dependent variables. Outliers may occur in both independent variables and dependent variables. Outliers in dependent variables may not be as problematic in some cases. One might have an outlying y variable that is distant from other y values, but is close to the regression line. This case would likely have little influence on the calculated statistics, as it would not change the regression line. One might also have a y value that is distant from the other y values, but near the middle of the x distribution. We can return to figure 14.1 and see such cases in A and B. As noted above, these cases are not likely to influence the results of analysis of covariances, but they might influence the intercepts. Outliers in the independent variables are thought to be much more troublesome. Again, returning to figure 14.1 C and D, we see that independent variables that are far from the mean can have substantial leverage and can change the results of an analysis. In these situations, as with the univariate outliers, graphical analysis can be helpful. Researchers should be encouraged to look at graphs such as scatter plots. Such an analysis can suggest outlying data points and allow researchers to examine other properties of the data, for example, linearity of the relationships between x and y. Statisticians have also urged researchers to look at the hat matrix. The hat matrix derives its name from the matrix that relates the matrix of observed y-scores to the matrix of predicted y-scores in matrix algebra. The most interesting portion of the hat matrix is the set of diagonal elements commonly referred to as the or simply the h values. At a conceptual level, there is one h value for each case in one's dataset. For example, recall our sample containing information on 300 accountants. Analysis of this data would yield 300 h values. Continuing at a conceptual level, the h values represent the weight that each case has on the overall regression coefficient. Values of h that are greater than 2 ln are thought to have high levels of influence. To illustrate, an applicant with an h of greater than 0.0067 would be worthy of note in our sample of 300. If the applicant Rebecca had an h value of 0.21, she might be an influential case and would deserve further attention as noted above. A second set of quantitative approaches to detecting influential cases is even more comprehensive. These approaches focus on both the leverage of the case, primarily a function of a case's value on x relative to the distribution of x's, and the outlyingness or residuals for the dependent variable. One way to conceptualize the process is to think of comparing the results of the entire sample with the results of the entire sample without the case in question. The case for using these approaches is best summed up by McClellan 2000 as he humorously notes that the really nasty observations, the ones that have greatly disproportionate influence on the overall model, are those that have both predictor and criterion values that are at least a little bit weird. The two most popular versions of this approach are Cook's D and D-fits, also known as the Welsh coup distance. In both cases, the techniques generate a statistic for each case that can be compared to a graph or benchmark to identify cases for attention as a possible influence. For Cook's D, there is a D value for each case in the dataset. Researchers can visually examine these cases to see if the largest D value appears to be a significant departure from the next nearest D values. In the case of D-fits, a value of more than 1 or 2 is thought to be large enough to deserve some attention. Several observations on these influence statistics are warranted. First, they are designed to focus on the results of the entire regression equation. That is, they examine the influence of outliers on overall results. They are not designed to focus on the influence of an outlier on a partial measure of covariance, such as one regression coefficient in the multiple regression. However, the DF-betas approach, which is conceptually similar to DF-fits, can examine the influence of outliers on individual regression coefficients. Second, and as noted above, DF-fits identifies influential cases using some benchmark statistic. However, there is no hard and fast rule for a benchmark value above which one can automatically delete cases. We discuss some guidelines for coping with outliers and influential cases below. There is one particularly important observation about using virtually any of the current outlier detection techniques. They are primarily designed to detect one outlier/influential case. The computations are somewhat involved in single outlier detection, as most of the techniques require a conceptually separate analysis of each data point. However, 2 or more outliers can easily mask each other with current approaches. The general principle of why it is difficult to find multiple outliers can be easily illustrated at the conceptual level by examining studentized residuals, although the logic also applies to Cook's D and DF fits as well. Let us assume that we have a situation such as F in figure 14.1. In this case, we note 2 outliers, the means of which are very somewhat different from the means of y, but very different from the mean of x. The independent variable might be a measure of job satisfaction, and the dependent variable might be a measure of intent to turn over. The two outlying data points belong to Laurel and Hardy, and while the computer is calculating Laurel's t-value, Hardy's outlying case is included in the estimation of the standard error and vice versa. So the estimate of the standard error is enlarged and the sensitivity of the test is diminished. Efforts have been made to overcome this problem, but the computational demands on computers are still extremely heavy for many datasets. The issue of masking has two important implications. First, this is one reason why examining relevant graphs is still thought to be quite important to detect outliers. Graphical analysis can help identify situations in which outliers are masking each other. Second, it is recommended that if one identifies and deletes or modifies an outlier, all relevant statistics be run again to allow for another outlier that was masked by the first. While calculating the relevant statistics a second time is a good idea to find subsequent outliers, it does not solve the problem of two or more outliers masking each other. It is also interesting to note that finding such outliers in more complex procedures such as structural equation modeling seems to have received markedly less attention than for multiple regression. Two researchers elegantly address the issue of influential cases in structural equation modeling. They argue that many researchers interested in structural equation modeling view the correlation matrix as an input/starting point to their analyses, and may tend to overlook influential cases within the matrix. This is in spite of the fact that influential cases can cause problems in CFAs, such as correlations being greater than 1. Rensvold and Chung suggest a jackknife-based method for detecting influential cases. In this approach, goodness of fit indices are calculated for the sample, with one case omitted each time. These end fit indices are then rank-ordered to determine which cases have the greatest effect on the model fit. Rensvold and Chung also noted that the same model-based approach can be applied to any specific parameter of the model under investigation. Meta-analysis may also encounter influential cases. Such cases can easily influence both the mean and variance estimates in a meta-analysis. For example, an unusually low correlation between cognitive ability and a measure of job performance might downwardly bias the mean correlation, and it might inflate the amount of variability in correlations observed in the meta-analysis. Meta-analytic analyses with small sample sizes are particularly sensitive to this situation. The inclusion of an influential case with an unusually low correlation might result in underestimating the predictive validity of cognitive ability tests, that is the truth score, and lead to erroneous moderator analyses. In order to cope with situations such as this, Huffcutt and Arthur in 1995 developed the sample-adjusted mean deviancy statistic, or SAMD. This is the only meta-analytic influence statistic available to researchers of which the authors are aware. It follows a similar logic to Cook's D, in which researchers visually examine the value of the deviancy statistic to isolate outliers. Its use has allowed identification of influential cases, for example, Vinscher, Shipnim, Switzer, and Roth 1998, and a straightforward case of using this statistic in a plot of deviancy values is available in the applied psychology literature. We urge meta-analysts to consider its use. Coping with outliers and influential cases. Coping with outliers and influential cases is perhaps even more difficult than detecting them, and there is considerable disagreement in applied psychology over how to handle this issue. While there has been a moderate amount of work in the realm of influential case detection, there has been less research on how to handle influential cases once they have been found. We attribute this state of affairs to two factors. One is that determining what to do with influential cases is not as elegant a statistical problem and may be less interesting to statisticians. A second factor may be that the existing influential case literature is largely from statistics and natural sciences. Rigorous studies, derivational or Monte Carlo, of approaches that might be applied in applied psychology are relatively few in number. This state of affairs might be problematic, as there are very few analyses of the implications of using various influential case detection approaches, especially if assumptions of the proofs that they were developed from have been violated. In overview, there are two sets of solutions to the problem of influential cases. Generally accepted guidelines. There are several fairly universally accepted guidelines for dealing with influential cases. First, researchers are urged to check the accuracy of their data. It is generally believed that a substantial portion of influential cases are mistakes in data entry. This suggests careful attention to checking influential values relative to the primary data. Second, researchers should be sure that their model is complete. It is possible that detecting one or more influential cases might suggest that researchers refine their measurement techniques or add another variable to their models. For example, a political science researcher was interested in understanding the relationship between democracy and income equality. The researcher measured a country's democraticness by recording the number of years that it allowed voting for national offices for all citizens. The analysis resulted in an influential case for the countries of South Africa. Other researchers measured the amount of democracy using voter turnout to solve the measurement problem. It is also possible that adding another variable to the model is an appropriate solution. Such a variable might explain the variance in the dependent variable that makes the case influential. Analysis of sales volume by salespeople might result in one or two influential cases. These salespeople might sell much more than others. One could visualize this in two influential cases instead of one. The variance in sales, including these outliers, might not be explained by cognitive ability or personality variables or any other part of the selection system. However, inclusion of the geographical area or density of customers in various districts might explain the variance. That is, when including customer density as a variable. Researchers are also able to report the results with and without the influence of outliers. The advantage of this approach is its simplicity. For some cases, there will be one or two influential cases identified by methods such as Cook's D or DF fits. One could report a correlation or regression model with and without these cases. The disadvantages of this approach are that it is hard to know which estimate is the best estimate of the relevant population parameters. It is also confusing if the presentation of the two analyses presents two answers to the research question. For example, what if the situation in 14.1c resulted in a strong negative relationship between a measure of job sat and intent to turnover without the influential cases? In contrast, the relationship with the influential cases is only slightly to moderately negative. It will be difficult to know which statistic is the best answer of the parameter. Interpretation may be even more difficult if only one of the analyses is significant and the other analysis is not. For example, the relationship in figure 14.1c might yield a statistically significant result without the influential cases, but the relationship with them is not significant. Researchers are also able to report their results with and without the influence of outliers. The advantage of this approach is its simplicity. For some cases, there will be one or two influential cases identified by methods such as Cook's D or DF fits. One could report a correlation or regression model with and without these cases. The disadvantages of this approach are that it is hard to know which estimate is the best estimate of the relevant population parameters, and it is also confusing if the presentation of two analyses presents two answers to the same research question. Right. Other options for influential cases. The decision to delete the influential cases or not to delete and then present one analysis has been hotly debated for decades, even centuries, in a variety of literatures. This issue is controversial in applied psychology. One school of thought argues for analysis of all data on the basis that each case is part of the same data set and important information is inherent within each data point. Ornall reported 29% of those surveyed in psychology endorsed this view. The other side of the debate is that data may be deleted if there are strong theoretical or methodological reasons for deletion. One example is a researcher who studied the relationship between cognitive ability and the amount of goods sold. He might identify an influential case and find this person is not a native English speaker, which accounted for his low test score, but did not influence his job performance. Ornall found that 67% of IO psychologists endorsed this position. It is important to note that this position requires documentation in research results. A third position in this debate is that researchers should strongly consider deleting influential cases based on their identification by the better detection methods. The use of Cook's D or DF fits and other such methods allow a rather dispassionate and well-documented approach to identifying influential cases. As such, researchers can often identify the influential cases. The logic underlying this position holds that in an analysis in a dataset, it is quite inappropriate to allow one observation to dominate or change the interpretation of the test of the data. Just as it is unethical to arbitrarily delete data, it is bordering on poor research practice to let one data point change the interpretation of all of the rest of the data. Interestingly, deleting a case brings the researcher in a small way into the realm of missing data that is covered in another chapter in his volume. See Switzer and Roth, chapter 15. Traditionally, researchers have deleted the entire influential case from analysis, and this results in losing all of the information in that case. If only one value in that case is problematic, researchers might consider inputting the single value that is causing the case to be influential. One might impute the value of that value using a missing data technique, that, for example, regression imputation, in order to save the rest of the data. However, the imputation process might become quite problematic as one deals with multivariate outliers and one has to impute a large portion of the data in that case. It might be easier to utilize this approach for univariate or possibly bivariate outliers. Research in this area would be highly interesting. It is also possible to transform the data to minimize the influence of an outlier. For example, positively or negatively skewed distributions are often transformed by some function such as a square root, and such an approach can minimize the mathematical differences between scores on a given variable to facilitate analysis. But then one has to interpret a transformed score, and it's not clear how decision makers will interpret such information. Winsorizing is a conceptually intriguing approach to handling influential cases. The concept underlying winsorizing is not to delete the case in question, but to modify its score so it is no longer deviant from other cases. Early research analyzed univariate statistics such as the mean and the standard deviation for fairly small samples. And there were a variety of mathematical rules to adjust deviant scores. For example, one rule was to set the deviant number to the next nearest number in the dataset. How strange. The advantages of winsorizing parallel the advantages of various missing data techniques. This approach keeps and does not modify other scores in a case when a univariate approach is used, and it preserves all of this information from possible deletion. The potential disadvantages include the difficulty of determining the bivariate and multivariate statistical space and how to modify cases in such a way as to change values and preserve much original data as possible. The approach is also not well documented or accepted at this time. However, further development of winsorizing algorithms and Monte Carlo examinations might prove highly interesting in the future. Differential weighting of the observations is also possible. Fields in the physical sciences have designed weighting schemes that provide differential weight to observations. For example, cases near the center of the distribution are given greater weight than those that are farther away from it. This is clearly a way to avoid deleting any observations, but there does not appear to be a strong history in applied psychology for differentially weighting individuals, and this approach would also benefit from future methodological study. Conclusion. We urge greater attention to the issue of outliers in influential cases. They can have strong influences on statistics such as correlations and CFA analyses. The first step in handling these cases is to detect them using both visual and statistical approaches. Visual approaches should include examination of univariate statistics such as frequency distributions and bivariate distributions such as scatterplots. Special attention should be paid to groups of outliers that may mask each other, as statistical techniques are vulnerable to such phenomena. Detection by statistical means should focus primarily on influential statistics such as DF fits or codes D. Once outliers are found, we suggest careful analysis of the accuracy of the data and the completeness of the model. When outliers must be dealt with further, we suggest deletion is often appropriate when there are potent arguments. For example, the case was not a part of the relevant population. Deletion might also be justified on the basis of using better influential case identifiers like DF fits, although this is somewhat more controversial. We also urge future research on other intriguing approaches such as winsorizing or imputing the values for influential cases. The examination of these alternatives should prove stimulating and may help offer other solutions to the problems of influential cases.